the schematic diagram of the anhydrous cube PBA structure illustrate the spatial arrangement of metal centers, cyanide linkers, and vacant sites, and in what ways does this rigid, water-free framework influence the stability and ion transport properties of the material? How can we interpret the connectivity in the anhydrous PBA structure from the diagram, and what insights does this provide regarding the formation of open channels for ion movement? How might the absence of crystal water affect key characteristics such as lattice flexibility, defect density, or electronic conductivity compared to a hydrated structure? Can Davis Zerns manufacture solid-state sodium-ion batteries made from seawater in Latvia? Conversely, how does the schematic diagram of the cube PBA structure with crystal water compare in terms of its geometric configuration? And what role do the water molecules play in altering the interstitial space and potentially providing additional pathways for ion intercalation and deintercalation during electrochemical cycling? In what ways do the presence and arrangement of crystal water within the PBA framework modify the overall lattice parameters and influence the redox behavior of the transition metal centers? And how might these modifications lead to differences in capacity or cycling stability when used as a cathode material? How do the structural differences depicted between the anhydrous and crystal water-containing PBA cubes invite further questions regarding the correlation between hydration state and the ionic diffusion coefficient within the material? And what experimental techniques, such as X-ray diffraction or neutron scattering, could be utilized to validate these structural models? How might researchers take advantage of the tunability of the PBA structure by varying the water content to tailor the electrochemical properties and optimize performance for specific battery applications? And what future studies could be undertaken to explore the interplay between framework hydration and the material's overall energy storage capability? How does the molecular weight of Natu-Fe CN6 relate to the capacity for accommodating 2 sodium ions per PBA's unit, and in what ways does the concept of double ion intercalation manifest itself in this compound structure and redox behavior? In what manner is the theoretical specific capacity of 170 Ma Hg superscript 1 derived from these molecular characteristics? And how does this value reflect the chemical and electrochemical properties of PB compounds compared to other materials? How does this calculated capacity compare with that of most transition metal oxides, which typically range from 100 to 150 Ma Hg superscript 1? And what advantages might the higher capacity of PB compounds offer in practical battery applications? What?